Hey friends, here we are for another fun adventure in Honors Pre-Calc or AP Pre-Calc. This is not really teaching us something new, it's just kind of tying together some concepts. It does point out that the three types of functions that kind of show up in every math course are linear, we have quadratic, and we have exponential. So, I mean, at this point in your math career, you should be fairly confident that a linear function looks like a line, thus the name. A quadratic function will result in a parabola. And exponential is something we haven't really dug into this year, but you have seen in the past. Oops, worst tracing job ever. Exponential growth is kind of what we're looking at now. We've been looking at these as if they were arithmetic because you have a consistent increase or decrease through addition. And then we've been looking at these because these mimic geometric sequences. So they wouldn't be connected in a line, but they would have dots that follow these paths. So we're going to look a little bit more at the exponential function aspect. So that's kind of the, oopsies, that's kind of the concept right here. So definitely these are the key concepts that you want to know and you want to be aware of the characteristics, what the pieces mean, and so on. So this is going to be an important part of your notes to be able to look back on and find later, because the rest is going to be examples. So let's dig into it just a little bit. An exponential function has this general form. And so this is very similar to what we've been doing in geometric, in that it starts with like an initial value that you got when you plugged in x equals 0. This we are calling r, but that is your growth factor. And your growth factor in an exponential function acts as the same as the common ratio does in our in our geometric functions. Okay, so in this scenario, we have a positive a, because like in all functions, if your a is negative, it's going to flip that or reflect that over the x-axis. So we're not tackling that right now, but in this picture, a is positive, because if it was negative, this whole thing would be going downward instead. So this is a positive a kind of a scenario right now. So this is telling you that exponential growth is going to require that growth factor or ratio value to be greater than 1. So that makes sense to me, because this is telling me that my growth factor is more than 1. And so that's like saying r equals is greater than 1. So you'd be multiplying by like a 2 or a 3 or a 5 or anything greater than 1. In that situation, your values, your numbers are going to get bigger. And they're going to get bigger faster. Because let's say it's a 2, things are going to double and then double and then double. And so it gets bigger faster and faster and faster. So we have to relate this back to the concepts from earlier in Unit 1, increasing and decreasing. So if you look at this picture, this exponential function is always increasing. Or the other option for these is that it would be kind of coming down from left to right, as you see over here. That scenario means that your growth factor is still positive, because you wouldn't have a negative growth factor. But here, your growth factor is less than 1, same as if your r was less than 1. So say you were using a half. If you multiplied your start value, cut it in half, and then half, and then half, and then half, it would mimic this exponential decay, we call it, when it's going down from left to right. And so in this first situation with exponential growth, this one is increasing forever, like on the entire graph. This is going to be increasing. And you can see with exponential decay, it's decreasing from left to right for the entire thing. So they are either always increasing or always decreasing. They do not have max or mins. So make sure you know exponential functions have no max, no min. They have no relative extrema. What about concavity? Concave up versus concave down. So exponential functions are either always concave up or always concave down. Again, no exceptions, no changes. So as a result, we know that these have no points of inflection. So it's just important for you to like visualize those graphs and be like, I can't look for points of inflection because there will not be any. I shouldn't be looking for max or mins because there will not be any in terms of relative. Because you would obviously, if you had a closed interval, you might be able to say, oh, hey, on a closed interval, this is my min and this is my max, but they aren't relative min or maxes, meaning like peaks or valleys on the interior. So then let's talk about end behavior. Again, a thing we have learned about in the past. Here, for an exponential function in general form, as the x values, your input values, increase or decrease without bound. Keeping in mind that if you have x values that are increasing without bound, that means this. It also is talking about the right end of your graph. If you have the limit of a function that is exponential or any kind of function, and you are decreasing without bound, and a couple of you keep getting caught with that on the test, so read carefully, that is asking about the left end of your graph. And then it's saying the outcome values, meaning your y's or your limit answers, will either increase or decrease without bound, meaning your answers would be positive or negative infinity, or they will approach zero. So you don't have a lot of options with the end behavior. You can see from this graph, like this is going up forever, this is approaching zero. Here, this is going up forever, this is approaching zero. If it was flipped over, it might be approaching negative infinity. So end behavior limit statements, this one's all funky monkey. I think that just didn't get downloaded properly, but you guys, I think, have it, where if you had the limit of a b to the x, which means an exponential function, as x approaches positive or negative infinity, meaning the ends, it will either be infinity or it will be negative infinity or it will equal zero. These are your three options for the end behavior of our exponential functions. We're not digging a ton into plugging in numbers. We are digging into their shape and their behavior. So let's try doing the example. So for the rest of this is example 1, 2, and 3. So let's get those knocked out, and then we'll be all ready to be experts on our homework. It says, write a limit statement. So that is actually my instructions for the end behavior. So if you look at this, this is your right end, this is your left end, this is going up towards infinity, this is going towards zero. When I go to write left end, I write the limit as x approaches negative infinity or decreases without bound. I'm supposed to write my exponential function, and in this case, the left end's approaching zero. For the right end, the x would be approaching infinity because on the x-axis, this is positive infinity over here and negative infinity as you go to the left. This is my specific function that we're talking about, and the right end of this goes up, so I would write it as infinity. Now, this one has a negative a value, so this one got flipped over and is underneath the x-axis, but it's still exponential in nature. The left end is heading downward, and the right end's heading towards zero. Both of those are legitimate options for our graph. So I'd say, hey, the limit as x approaches negative infinity, because I want the left end behavior of this function, and keep in mind that this had a negative a in front of it or it wouldn't be upside down. And that one's going down, so my answer is negative infinity. The right end is approaching zero. So the limit as x approaches positive infinity, guaranteeing that I'm talking about the right end, approaches zero. So this is just tying the concept of an exponential graph, what it looks like and how it behaves, to our previous concepts of end behavior and limit notation. Now here you have to do some thinking because there's not a graph. This is your B value. B value is located where the R value was when we did this as geometric sequence. Now, this value of 2/3 is less than 1, but still positive. So this is going to be a decay situation. And so if you think about what that would look like, then you are going to have something that's coming down from left to right. It doesn't cross zero because everything approaches zero, infinity, or negative infinity. So The left end of this will be going up, and the right end of this will be the one that's heading towards 0. So when I go to write this out, I'm going to write the limit of function g as x approaches negative infinity for my left end. And since that's going up, I get an answer of infinity. Because keep in mind, this side's describing what x is doing, and this side is describing what the y values are doing, like what you see on the graph. The right end is notated like this. You don't need the plus sign of this function. Since the right end's heading towards 0, that's what I write. Okay, so let's analyze this guy a little bit and see what would this look like. I don't have any negatives, so it's not flipping around left or right yet. But I have an R value, which is the same as like the B value, I guess, your growth factor of 5, which is definitely greater than 1. So this is going to be a growth. And so it's going to be, as x goes larger, this is going to go up from left to right with that floor of 0 that it never really hits. So my left end is heading towards 0. This is h of x, so I'm going to do that accurately. You do want to pay attention to that on the FRQs, that you write it to match what they're talking about. So the limit of this function as x approaches negative infinity will be the 0 end, and then the right end's going up. So the limit of this h function, which I just keep really wanting to write as an f, so now it looks weird, but I don't care. As x goes to positive infinity is talking about the right end's going up, that's going to be positive infinity. Also not written well, also still don't care. Okay, now what are we doing? Now we are going to determine if each exponential function is increasing or decreasing, concave up or down, keeping in mind that it never changes. If it's increasing over the whole domain. If it's decreasing the whole entire time. So here I get to use my eyeballs. If I go from left to right, my values are going down from left to right. So my graph would be decreasing in value. And you can look at the concavity, it's opening upward, and so it's going to be concave up. These are just eyeball activities, so I can handle this. Here, my values are decreasing. They're going down and down and down as you go. And so I have decreasing values, and the concavity is opening down as well. Now, when you can't see it, it stops being fun. So you have to think a little bit. Here, my growth factor, which is like my ratio, is greater than 1. And my A is positive. So I can kind of just sketch myself like what I know this might look like. It doesn't have to be perfect. I just have to know that this is exponential growth. So I have something that looks like that. That is going to be concave up, and my values are increasing as I move along that function. Last one's going to throw us a couple little curveballs here. For 1, my B value is less than 1, so this is going to be decay, but I also have a negative A, so this is going to get flipped over the x-axis. So I'm going to just kind of walk myself through that to make sure I don't mess it up. And so what I'm going to do is, in my little ghost pen, I'm going to go ahead and draw what would be a decaying function. But that's not really what I need. I need to flip that over. And if you flipped that over the x-axis, you're going to end up with something that looks like this. So this is the one that I want to look at. This is my m of x. That thing is concave down. And that thing, if I follow the values from left to right, they are increasing. So you have to be able to take what you see in a function like that and know how the outcome will look enough to determine concavity and increasing or decreasing. Okay, last thing. Selected values of functions are shown in the tables, and we see these table problems a lot. You got to kind of think about what they want you to do. We are deciding if it's linear, quadratic, or exponential, or none. Okay? Now, keep in mind that you want to watch for the interval values of the x's to stay the same. I believe these do, like these all go up by 5, so we can just pay attention to the y's. These keep going up by 3. So as long as you have equal intervals, these are going up by 2. I don't care that they're going up by 2. I just want to make sure that they're not spaced out weird. And these are going up by 1. So now we can focus on what are our y values doing. So these, if I look at these y values, I can kind of find the pattern here, and I can see that these are going up by 2, then this is going up by 4, by 8, by 16. Okay, so that is certainly not linear. That is going to be where I've got some kind of like multiplied by 2 pattern going. If you can see this, it goes up by 2, times 2 is 4, times 2 is 8, times 2 is 16. So since I have like a multiplication pattern, we've said it before that it was like proportionate. That means my function is going to be following an exponential type of path. Because exponential is repeated multiplication. It's like the same as the geometric style that we talked about. Here, when I look at these values, I can see that this went down 7, as did this, as did this, as did this. And so here I have that, like these are constant. And we kind of started the year with that. Because these change in y values are the differences are the same. So that's ironic, the differences are the same. Actually, the word they'll use is constant. That's going to indicate that this is linear. These are going up, or excuse me, these are going down by 7, down by 7, down by 7. That would generate a line. Okay, here, let's see if we can figure out what's going on with these guys. This is going down by 24, and then down by 12, and then down by 6, and then down by 3. So when I look at these, they're clearly not the same, so it isn't linear. And I can see that I'd take half of this to get to 12, half of 12 to get to 6, half of 6 to get to 3. So I actually have a geometric pattern there. And that geometric pattern is like a multiplication pattern again. And so because of that, that's going to be an exponential kind of a pattern, or an exponential type of a function. Okay, here on the last one, this went up 2, this went up 4, this went up 6, and this went up 8. So they're not the same, obviously, but they're also not multiples of each other. Like I would have to go 2 times 2 to get here, but if I did 2 times 2 again, I'd get 8, not 6. So it's not really following a linear pattern because they're not the same number, and it's not really following a geometric or exponential-ish kind of thing because they don't multiply to become each other. So the way that we had learned to determine if something was quadratic, which is our third choice on this, is to check our second set of differences. So from 2 to 4 is up 2, from 4 to 6 is up 2, from 6 to 8 is up 2. So my second set of differences is the same, and that's going to make this one quadratic because my second set of differences, meaning the differences or changes in my y, are equal or constant. And so that means this is quadratic. Keep in mind that having a second set of differences that are constant means that your first differences are linear, because your first differences are going up by 2, up by 2, up by 2. So those two statements mean the same thing. Your second set of differences are constant, means the same as your first differences being linear. So you want to be able to recognize both of those things as indicating that that set of numbers or values would be quadratic. So there's not a lot of new information in here outside of maybe refreshing your memory on what the graph looks like, but it is tying all the concepts we've done from the tables to the graphs to increasing to concavity in with this new information. I'm just noticing that I missed a little spot here, so let's just fill these in. A represents your initial amount. So in terms of like what we've done in our geometric sequences, that would be like your A sub 0. B represents the base, which is the thing that you are raising to the power. We've been calling that the common ratio. So in geometric sequences, if we could connect the dots, we'd be getting these graphs that are the same as the exponential functions. All right, that's a lot. Hopefully that helps. Bye, guys.